hot Jupiters, gas giants that shouldn't exist where they exist. Our Jupiter, orbits the sun once every 12 years, safely out past the asteroid belt. A hot Jupiter does the same job in 4 days, sometimes less. Some of these worlds finish an entire orbit in under 20 hours, close enough to their star that their cloud tops bake at over 2000 degrees Celsius. That's hot enough to vaporize iron. And these planets do vaporize iron, literally, iron rains down through their atmospheres. And on the hottest ones, it condenses back into liquid metal clouds. Fittingly, this was the first type of exoplanet we ever confirmed around a normal star back in 995-51 Pegasi b, detected by the tiny gravitational wobble it induced in its star as it whipped around in just over 4 days. Astronomers at the time assumed a real solar system had to look roughly like ours, small rocky worlds inside, big gas giants far out. A giant planet that close broke the assumption on the very first try. Here's the part that should genuinely bother you. Gas giants aren't supposed to form this close to a star. The heat should have blown their hydrogen away before they ever got big, which means every hot Jupiter we've found took shape somewhere far out in its solar system, cold and slow, the way Jupiter did, and then migrated, spiraled inward, crossed the entire orbital real estate of its own system, potentially flinging smaller rocky worlds into the void or into their sun on the way past. WASP negative 12b, one of the most extreme examples, is so close to its star that it's shaped like an egg, stretched by tidal forces, actively losing its atmosphere into a comet-like tail of gas. It's being eaten slowly in real time. Astronomers estimate it has about 10 million years left before its star finishes the job. 10 million years sounds long. On a stellar clock, that's a few final breaths. Let that sink in. Some planets don't die in fire or ice. They die by proximity, evaporating a little more every single orbit, and we can watch it happening from here. And WASP negative 12b isn't alone in this. HD 209458b, nicknamed Osiris, was the first exoplanet ever caught losing its atmosphere directly, streaming a tail of hydrogen gas that stretches for tens of thousands of kilometers behind it, like a comet built from an entire planet's air. Some hot Jupiters even show glowing sodium and iron in their upper atmospheres, detected by starlight passing straight through the escaping gas as the planet transits. We are, in effect, watching a slow motion autopsy of a planet that hasn't finished dying yet, from tens or hundreds of light years away, one transit at a time. But if a planet surviving that close to a star feels unlikely, wait until you meet a class of planet that shouldn't exist at all by mass alone. Super Earths. The name undersells what these actually are. They're not necessarily habitable, and they're not necessarily Earth-like in any meaningful way. Super Earth is just a size category, rocky worlds between 1 and roughly 10 times Earth's mass. No solar system planet fits in that gap. Not one. Earth is 1.0. Neptune, the next planet up by mass, is 17. Super Earths fill a category that literally does not exist in our own backyard, which means everything we know about how they behave, we learned from other stars. Here's the twist: because they're bigger, their gravity is stronger, sometimes over 3 times Earth's. Stronger gravity means a thicker, more retained atmosphere, and it means volcanic activity that never really stops, because a bigger planet holds on to its internal heat for billions of years longer than a small one does. Some super Earths may have oceans hundreds of kilometers deep, not because they have more water percentage-wise, but because a bigger sphere holds more of everything, water included, stacked in layers under crushing pressure. Take 55 Cancri e, a super Earth roughly 8 times Earth's mass, orbiting so close to its star that a year there lasts 18 hours. Its dayside likely tops 4,000 degrees Fahrenheit, hot enough that its surface may be an actual permanent lava ocean. Some models suggest its interior, under that heat and pressure, could crystallize carbon into diamond. We'll come back to that idea. It gets stranger. Newer instruments are starting to actually smell these atmospheres, not just measure their size. The James Webb Space Telescope has picked out carbon dioxide, water vapor, and even hints of sulfur compounds around super Earths dozens to hundreds of light years away by reading the exact wavelengths of starlight that get absorbed as it filters through a planet's air during a transit. We are not guessing what these atmospheres are made of anymore. We are reading their ingredient labels from data collected as starlight bends around a world we will never visit. Other super Earths sit nowhere near their star at all. LHS 1140b, roughly 7 times Earth's mass, orbits comfortably inside its star's habitable zone, and its size alone means it could hold on to a thick, dense atmosphere far longer than a smaller world could. Bigger doesn't just mean hotter or more crushed by gravity, it can also mean more durable, a planet built with enough mass to keep shielding itself against the slow erosion every atmosphere eventually faces. But bigger isn't always simpler. Sometimes more mass means a completely different category of planet altogether, one that isn't quite rock and isn't quite gas. Mini-Neptunes, the most common planet in the galaxy, and one your solar system doesn't have a single example of. Bigger than a super Earth, smaller than Neptune, wrapped in a thick hydrogen and helium envelope over a rocky or icy core. Kepler's data suggests planets in this size range, roughly 2 to 4 times Earth's radius, may be the single most common type of planet orbiting sun-like stars in the galaxy. Statistically, mini-Neptunes could outnumber every other planet type combined, and we have 0 of them here. Some astronomers split this category further into gas dwarfs with mostly hydrogen envelopes and Haitian worlds, a proposed subtype with deep global oceans sealed under a thick hydrogen atmosphere, warm enough at the surface to stay liquid despite crushing pressure from above. Negative 18b, roughly 8.5 times Earth's mass, is one of the leading Haitian candidates, and its atmosphere has shown tentative signs of carbon based molecules that on Earth are only produced by living organisms. Tentative, contested, but enough to make an entire category of planet suddenly worth a much closer look. Here's the thing that should stop you. The gap between super Earths and mini Neptunes isn't gradual. Astronomers call it the radius valley, a genuine scarcity of planets at a specific in between size, like nature avoided that size on purpose. The leading theory, young mini Neptunes get stripped by their star's radiation. If they hold on to their gas, they stay a mini Neptune. If they lose it, they shrink down into a bare, rocky super Earth. The same planet, at 2 different points in its life, can look like 2 entirely different categories, which means the type of planet you're looking at might just be a phase, not a fixed identity, a stage in an ongoing process, frozen at the moment we happen to observe it. GJ 1214b, one of the best studied mini Neptunes, has an atmosphere so thick with haze that telescopes have struggled for over a decade to see past the clouds to whatever lies underneath. We don't actually know if its interior is rock, ice, or something stranger. The planet is quite literally hiding its own identity behind its own weather. And if a planet's category can change under its own star's light, imagine what happens to a planet with no star at all. Rogue planets. Worlds with no sun, no orbit, no home. Picture Earth, but flung out of the solar system entirely, drifting alone through interstellar space forever. That's a rogue planet, a fully formed world, sometimes Jupiter-sized, sometimes smaller, wandering the galaxy untethered to any star. Some form the way stars do, collapsing from gas clouds too small to ignite fusion. Others were born in a normal solar system and got gravitationally ejected, flung out by a close pass with a giant planet or a passing star, sent hurtling into the dark at speeds that never slow down because there's nothing left to orbit. Here's the estimate that should unsettle you. Some studies suggest rogue planets could outnumber stars in the Milky Way by a factor of several times over. Billions, possibly trillions, of worlds with no sun, no daylight, no seasons, drifting in permanent night across distances so vast that most will never pass near a star again for the rest of cosmic time. The math behind that estimate comes from a technique called microlensing. Watching a rogue planet's gravity briefly bend and brighten the light of a distant background star as it drifts past, a flicker lasting hours or days that's often the only evidence such a planet ever existed. No orbit to track. No repeat transit to confirm it. just one fleeting distortion in starlight, and then the planet moves on into the dark again, unlikely to ever be seen a second time. But here's the fact that changes everything about how we imagine them. A rogue planet isn't necessarily dead. If it's large enough and has enough radioactive material in its core, it can generate internal heat for billions of years. Heat that, under a thick enough atmosphere or an ice shell, could theoretically sustain a liquid ocean. No sunlight required. Life, if it exists there, would have evolved in total permanent darkness, powered entirely by the planet's own leftover heat from formation. Let that sink in. Somewhere out there, right now, a world the size of Earth could be drifting through the void between stars, no sun in its sky ever, possibly warm inside, possibly alive, and utterly, permanently alone. We've actually caught a handful directly. CFB Desire 2149 negative 0403, a Jupiter sized rogue discovered drifting with no parent star, sits roughly 100 light years away and radiates only its own leftover formation heat in infrared light, invisible in ordinary visible wavelengths. Finding these worlds at all means scanning the dark for the faint glow of a planet with nothing else lighting it up. No reflected starlight, no daytime, just a body slowly cooling in the black, one of possibly billions we'll never manage to spot. Not every extreme world needs to lose its star to become inhospitable. Some worlds are close enough to a star that the surface itself simply melts. Lava worlds. The dayside is a permanent ocean of molten rock. These are planets, often super Earths, orbiting so close to their star that surface temperatures exceed the melting point of rock itself, somewhere around 1,300 degrees Celsius. Not volcanic in patches. Not has some lava. The entire dayside continuously is liquid stone. Cato negative 141 Ebe, one of the most studied examples, is thought to have a rock vapor atmosphere, meaning the air itself is made of vaporized minerals, and where that vapor cools and condenses, it may fall as rain made of pebbles. Here's the part worth sitting with. Wind on a lava world can move molten rock the way wind moves water on Earth, generating waves on a literal ocean of magma, driven by supersonic winds that models estimate could exceed 5,000 kilometers per hour on the planet's terminator, the line between day and night. That's roughly 4 times the speed of sound. A hurricane of scorched air dragging a tide of liquid stone behind it. The one fact that changes everything. On a tidally locked lava world, the night side can be 1,000 degrees colder than the day side, meaning the same planet could have solid rock on one hemisphere and an ocean of fire on the other, separated by a boundary line where stone is actively melting and freezing in real time forever because the planet never rotates enough to let either side cool down or heat up further. A permanent boundary between molten and solid, between two different planets wearing the same globe. Coro negative 7b, one of the first lava worlds ever confirmed, may lose so much surface material to evaporation that some of what boils off its day side could theoretically drift around and refreeze as mineral snow on the night side. A planet very slowly redistributing its own crust through the sky, one vaporized rock at a time, over geological timescales too long for any observer to watch, start to finish. Not every close, hostile world is made of fire, though. Some of the strangest are made almost entirely of water, ocean worlds. Not a planet with an ocean, a planet that basically is one. Earth's oceans, for all their vastness, average about 3.7 kilometers deep, a thin film compared to Earth's radius of 6,371 kilometers. An ocean world is different in scale entirely. Models of planets like GJ 1214b suggest oceans that could run hundreds of kilometers deep, sitting atop layers of exotic high-pressure ice. Not the ice in your freezer, but forms of ice so compressed they remain solid at scorching temperatures, stacked below the liquid layer like geological strata made of water. Here's the twist that breaks the intuition. Deep enough under crushing pressure, water ice can exist at temperatures over 300 degrees Celsius and still be solid, a phase called ice 7. So an ocean world's interior might look like this. Liquid water on top, then a shell of hot solid ice underneath that, then possibly a rocky core below that. Water in 3 different states, in layers, on a single world, none of it behaving the way water behaves on Earth. The fact that should genuinely bother you, an ocean this deep would almost certainly cut off any seafloor from the water above it. No mineral exchange between rock and ocean, the kind of chemistry believed to have helped spark life on early Earth, a planet drowning in the exact ingredient we associate with life, potentially rendered sterile by too much of it. Too much water, it turns out, might be its own kind of desert. Enceladus and Europa, moons rather than planets, give us a nearby preview of the idea icy shells over hidden oceans kept liquid by tidal flexing instead of starlight. Scale that concept up to an entire planet, add a star's worth of heat on top, and an ocean world stops looking like paradise and starts looking like a pressure chamber, one where the very thing we search the galaxy for might exist in such overwhelming abundance that it cancels out the chemistry needed to use it. And an ocean world's fate, hot on one side, changed forever by its star, brings us to planets that don't just have a hot side. They only have a hot side, permanently. Tidally locked worlds. One face burns, the other never sees light. Gravity, given enough time, synchronizes a planet's rotation with its orbit, the same reason the moon always shows Earth the same face. Around small, dim red dwarf stars, which make up roughly 70% of all stars in the galaxy, planets in the habitable zone orbit so close that tidal locking happens fast, often within a few 100 million years. The result, one hemisphere in permanent, unbroken daylight, the other in permanent, unbroken night forever. No sunrise, no sunset, ever for the entire life of the planet. Here's the escalation. The dayside could reach blistering, water boiling heat, while the night side plunges to temperatures cold enough to freeze the planet's entire atmosphere solid onto the ground, meaning the air itself could snow out of the sky and never sublimate back, unless something moves that air around fast enough to keep it circulating. Here's the fact that changes everything. Climate models suggest that on some tidally locked worlds, ferocious permanent winds, driven by the extreme temperature gap between the two hemispheres, could carry enough heat from dayside to nightside to prevent total atmospheric collapse, creating a narrow habitable ring at the terminator, the twilight boundary between burning and freezing. Not a hemisphere, a ring, a strip of permanent dawn, maybe a few 100 kilometers wide. That might be the only place on the entire planet where liquid water and breathable air could coexist. An entire world, and the only livable place on it is a border, a seam between two forms of death, holding a thin margin of survivable weather for as long as the wind keeps blowing. Proxima Centauri b, the closest known exoplanet to our own solar system at just over 4 light years away, is very likely tidally locked for exactly this reason. It orbits a red dwarf so closely that a year there lasts just 11 days. It's the nearest other world we know of, and depending on what stands in its terminator ring, it may also be one of the strangest. If a planet can be split between fire and ice by its rotation, imagine what its own crushing internal pressure can do to plain carbon. Diamond planets, the most literal treasure in the galaxy, and it's a curse. Most rocky planets, Earth included, form from a chemistry dominated by oxygen, silicate rock, basically sand and stone, all the way down. But some planetary systems form from carbon-rich material instead. Change the recipe, and you change the planet. In a carbon-dominated world, instead of layers of oxygen-bound silicate rock, the interior could be built from graphite, and deeper down, under pressures found only near a planetary core, carbon crystallized directly into diamond. 55 Cancri E, the same super-Earth we mentioned earlier, the one with the lava ocean, has been proposed by some models as a possible carbon-rich world, meaning a meaningful fraction of its mass, by some estimates as much as a third, could theoretically be crystallized carbon. Not a diamond vein, not a diamond deposit, a significant portion of an entire planet's structure. Here's the fact that changes everything. A world built this way would be geologically almost inert. Diamond doesn't behave like the rock that drives Earth's plate tectonics, volcanism, and carbon cycle. It's rigid, thermally strange, resistant to the slow churn that keeps the planet's crust recycling nutrients and regulating climate over deep time. The very substance that makes it precious to us would make it nearly dead as a system. locked in structural stillness, while our kind of rocky planet keeps grinding, melting, and renewing itself. The most valuable material on Earth, by weight, might just be ordinary planetary furniture somewhere else, and the planets made of it might be the least alive worlds in the galaxy, dressed in what we'd call the ultimate reward. PSR Joan 1790 negative 1438b, an extreme case orbiting a rapidly spinning neutron star, is suspected to be the crystallized leftover core of a star that had almost everything else stripped away. So dense and carbon rich that some researchers have described it, only half jokingly, as a diamond roughly the size of a planet. It's a reminder that Diamond Planet isn't poetry here. In some cases, it may be closer to a literal description. 8 worlds, 8 ways for a planet to be nothing like home. Here's what ties every one of them together: hot Jupiters migrating inward and getting slowly eaten by their own star. Super Earths, a size category so common out there, it doesn't exist here at all. Mini-Neptunes, possibly the single most common planet in the galaxy, caught mid-transformation by a radius valley that turns one type of world into another. Rogue planets, wandering starless and possibly warm and permanent dark, maybe outnumbering stars themselves. Lava worlds, split down the middle between an ocean of molten stone and a frozen dark side. Ocean worlds, drowning in the very substance we search for as a sign of life. Tidally locked worlds, surviving only in a thin ring of twilight between fire and ice. And diamond planets, built from the rarest material we know, and possibly among the most geologically dead worlds that exist. Every one of these is a planet. Every one of them is nothing like the 8 we grew up naming in order from the sun. And the galaxy holds an estimated hundreds of billions of them, most of which we will never see directly, only infer from a flicker of starlight dimming for a few hours and never coming back the same way twice. Over 5,000 exoplanets have been confirmed so far. Thousands more sit in candidate lists, waiting on follow-up observations to be certain. And that's from surveying a genuinely tiny sliver of one galaxy out of an estimated 2 trillion galaxies in the observable universe, each one presumably hosting its own uncountable share of hot Jupiters, rogue wanderers, and diamond cores. We have barely opened the catalog, and the catalog is already too large to finish reading in a human lifetime. Here's the part that should genuinely bother you, one last time. Earth, mild, rotating, watered just enough, neither melted nor frozen, orbiting a star that isn't trying to strip its atmosphere away, isn't the default. It's the outlier. Statistically, structurally, chemically, it is the strange one. Every planet on this list is, by the numbers, more typical of what a planet becomes than the one currently under your feet. No permanent daylight side burning away its atmosphere. No crushing global ocean sealing off its own chemistry. No orbit so tight its own star is quietly disassembling it, one evaporated layer at a time. Just one rocky, mid-sized, unremarkable-looking planet, third from an unremarkable star, in an unremarkable arm of one ordinary galaxy, somehow landing in the extremely narrow window where none of the extremes apply at once. Every category on this list is a way a planet can fail to be habitable. Earth is the rare planet that didn't. Not bad for stick figures on a rock.